Hi, good morning, JN. So can you hear me clearly? Nice to see. Happy birthday to you. Okay. I think we are ready to start our event. So good evening to our viewers in Asia and Australia. Good afternoon to our viewers in Europe and Africa. And good morning to our viewers in North and South America. On behalf of the panelists, Dr. Kota, Dr. Arun Srinivasa, and I, Prakash Thamburaja, we welcome you to this truly special global webinar in honor of our dear friend and colleague, Dr. JN Reddy. We are conducting this special seminar to celebrate Dr. Reddy's 75th birthday today. So Dr. Reddy, on behalf of all of us, we wish you a very happy birthday and many more happy returns to the day. Okay, before Dr. Reddy presents his seminar, the panelists have prepared some questions for Dr. Reddy to answer, and these questions have been in the minds of the panelists for quite some time, and probably in the minds of many others too. So today's special seminar is the perfect opportunity for us to ask Dr. Reddy these questions. So to kick off this event, we now have one of our panelists, Dr. Kota, to ask these questions. So Dr. Raj, the floor is yours.
Good morning, Prakash, and many happy returns of the day, Dr. Reddy. I mean, I consider you the Lord of Academia. I know you have been in the United States for a long time. You have come here long ways for your grad school. So I'd like to start there and kind of preface the meeting with asking you, what was your grad school experience like?
Options. Oh. Speaker options.
Yeah, so you are a host. I can.
No. I mean, the speaker you should put on should be.
So that's us.
But I don't know if it is right one. That's what. So Prakash, can you hear me?
Perfect, Jan. I can hear you.
Okay, great. Okay, I'm sorry we got interrupted. To answer your question, so I came to Oklahoma State University in Stillwater. It was really, it is still a wonderful campus, beautiful campus. I enjoyed being there. But the heart of the question asked is how I enjoyed it. You know, I went through 5-year integrated course in India compared to 4-year integrated course now. So I had a very good preparation. So the courses were not that challenging, I have to say that. So then what I did is I really directed my attention to new baby on campus, which is IBM 360 computer, because I never heard of computers and I never knew anything about these machines. So I started learning by self-reading Fortran books and then started coding assignments. So I was taking a course on vibrations at that time. So I started, programming the assignments I would do by hand. And then I also compute the eigenvalues, eigenvectors using the IBM 360 computer. Of course, those days you have to punch cards and feed that the cards to the computer. So, and then I would attach the output from, not only I'm verifying my hand calculations, but I also add that to the assignment I submitted. So the professor was very impressed. He said, you should go do PhD with J.T. Oden, who is already very famous in finite elements. So that is how it paved my way to write to Professor Oden. And then I joined, and then that is a history. So my graduate school, especially the time I spent in Professor Oden's group, was very fruitful. As many of you know, that it led to 2 books with him and several, landmark papers. So overall, my graduate education was a very good foundation for what I am today.
That was great, Dr. Reddy. Thank you. Past your grad school, I know it's an older generation kind of time frame. Like 75, the United States was completely different back then, and your grad school experience might have been completely different with most of the recent graduates. But back then, before the computer generation, right? What was your first experience like writing a paper?
Oh, it was so. What very first assignment that Dr. Gordon gave me was to read something about variational principles. So, with my background in primarily in mechanical engineering, that was the first introduction to kind of mechanics type research. So, I went through many books, and including the mathematical books that talk about functional analysis theoretics for constructing quadratic functional, finding Euler-Lagrange equations, and so on. So that led, and then he asked me to give a seminar to the group. So that was the first group seminar that I gave, and he was very happy that I did my homework right and came up with some ideas, and that led to one landmark paper that I wrote with Dr. Oden is on the what do you call dual primal variational principles in mechanics. That included 7 primal variational principles and 7 dual variational principles. And many of those variational principles, even though people may have not realized, but they are the foundations or the places where you derive the finite element models of various kinds, including the hybrid and mixed. So that kind of gradually led to a dissertation topic on mixed variational principles and mixed finite element approximation of boundary value problems in mechanics. So that was, again, the research I started was kind of derived from what I learned by reading a lot of books and papers on variational principles. And that naturally led to the questions that were not answered before, was especially existence, uniqueness of mixed variational principles in mechanics.
That should have been quite an experience there, Dr. Reddy. You should have had, since the number of publications and being the top cited researcher, you should have had a lot of experience in publishing starting then. And I don't know how that kind of molded you. I mean, I'm sure the first experience might have given you the chance to mold yourself. And that brings me to my next question. Writing paper, publishing it, submitting it to a journal, getting a reviewer comments, etc., that's quite a process. When we come to your next biggest achievement of writing books, right? I mean, that's what makes you the most popular man, is by the number of books you wrote. So what was your experience, or how did you get your first idea of writing a book?
Okay, so this is a very interesting thing to talk about, especially I never thought I would be writing books. So the very first 2 books that co-authored were with Professor Oden. He was very kind and gracious to me by asking me to co-author 2 books. One actually directly connected to my dissertation. Title of the book is Variational Methods in Theoretical Mechanics, published by Springer in 1973-74, just before I completed my PhD, officially 1974 summer. But so these books, first 2 books, were really derived from research, working. Much of the contents of these 2 books are self-taught. And that includes Dr. Oden also. He was trying to become a more mathematical in his work. Primarily, he was a civil engineer. He also graduated with a PhD from Oklahoma State University. It's a coincidence, but he's a very creative researcher. And so he was kind to let me work with him on these 2 books that led to, gave me the, I would say, the much needed incentive, and also think about how to bring your own knowledge to other people and understand the contents in a way that they can grasp. So that being the case, I never thought again I would write another book until I started teaching. So all of the books, with the exception of one or two, all of the books came from my teaching. So I was not thinking of writing the books. See, for example, the book that I wrote on finite elements, which is probably one of the three most cited books in finite elements, it has been a lecture notes kind of thing I taught from 1975 through 1982 or 83. I was doing this at Oklahoma, University of Oklahoma, which is different from Oklahoma State. Then when I moved to Virginia Tech, I was still teaching, but I started with using Zinkevich's book, and then when I found it not very good for a textbook, I moved on to other books. But soon it was very clear that I had to write a lot of notes to make myself comfortable lecturing and also making the students understand it. So in the process, I really wrote a lot of notes. So one time, Professor Oden visited me for a seminar. So he, like a parent would ask, and he asked me what I was doing, and I discussed with him about the research I was doing on composites. That was the first thing that I did different from what I was doing during my dissertation. Then I was showing my lecture notes on finite elements. So he immediately said, "Oh, JN, you should really publish this because this is very good. Students will appreciate it." So I said, there are so many of you great people. I don't think my book is going to be that important. So, but he said, no, it will serve the students for sure. So I continued that. And when I joined Virginia Tech, I taught for a couple of more years. I joined there in 1980. So in 1982 or 83, I submitted the manuscript to McGraw-Hill, Wiley, and I think even Prentice Hall. And all of them gave contract, but I accepted one from McGraw-Hill. So you can see that is a typical way that I got into writing books. I would teach, I create a lot of notes, and those notes become a book. And the last one, or the most latest one that I did was continuum mechanics. So again, I never thought I would write a book on continuum mechanics, but I taught continuum mechanics almost as many times as finite elements at Virginia Tech. I was sharing this course, and I, with the department at the time there, and he was very kind to ask me to also teach, and sometimes we would have two sections. And at Virginia Tech, the graduate students from almost all departments, of course, including mechanical, aerospace, civil, would take courses from mechanics faculty. I was in engineering science and mechanics department. So we would have anywhere from 30 to 60 graduate students in finite elements or continuum mechanics. So when I came here, I didn't teach for almost 10 years or so. When it fell into my lap, I started teaching and putting all those notes together. And then students said, we really like to see this in the book, form of a book. So that's how, again, at the time, one of the publishers was Cambridge University Press publisher, Peter Gordon, visited me. He said, "Oh, JN, we would love to publish your book." So that's how it ended up. So in summary, I have authored or co-authored two kinds of books. One that were derived from research, and those are very few of the books. And first two belong to that category. And there may have been a couple of others, one with Dr. Arun Srinivasa on smart structures. But then majority of the books, they came because of my teaching, occupied with the, rather passionately how to make it more understandable, easy to follow type courses. So in that process, I was able to write these books. And I feel very, very satisfied, as much as through research publications, but books are also going to be there forever and will cater to the needs of many young people around the globe.
Oh, thank you for that, Dr. Reddy. I think a lot of your old friends, maybe your grad school mates and maybe even undergrad mates might be joining the meeting. Just one last interesting question before we start the webinar. This is from Ramana Reddy. And how did Osmania University prepare you for higher education, and what courses were you interested?
Okay, so I will say a few words later on in my presentation, but I think, see, everyone, this has been my philosophy, even my own students here and elsewhere, they took courses beyond what is required of them in terms of course requirements, because once you leave the university, you will not have the opportunity to take courses from organized way from top-notch faculty members. So you must take courses, more and beyond the required courses of the curriculum or your advisor says, because you need to have that breadth as well as depth in subjects. So my advice to all the young people, not only graduate students, but young faculty, they should let their students to take as many courses in the broad area of their education, and so that they can, extend and also go beyond what they did for their dissertation when they join a company or a university, because this kind of organized learning doesn't happen unless you are a very, very organized person, and you have to have time. So that combination is rare, because once you join a company or university, you have other responsibilities that prevent or prohibit you from doing those things. So my advice for people is to learn the subjects while you are in the university, and knowing the mechanics, especially topics. By the way, the word mechanics I'm using in a broader context. It includes everything under the sun. So whatever area that you work, you must take those courses and understand, so that you have the confidence in fundamentals and also feel that you know how to extend or how to apply. So this kind of thing doesn't happen unless you put your heart into it. So knowing is really the knowledge, and it increases your ability to understand and attack problems. And of course, in real world, there are a lot of things that happen, or in your own way, that you try to attack the problem. See, formulating a problem is the most difficult task, and it may require multiple courses in your background, not just one or the other. It may require more than one. So I am trying to say that you must have those subjects so that you can attack or formulate the problem and go on to solve in whatever way you're planning to do, whether you use computational methods or doing experiments. So knowing the subjects is really very, very important, independent of the type of research you do, whether it's experimental, computational, or just purely theoretical mechanics.
Fantastic. Yeah, I'm sure that is helpful. Yeah, right before we start the webinar, I'd request all of the attendees to post your questions in Q&A section, not in the chat section, so that once the webinar is complete, Dr. Thamburaja can post all of your questions to Dr. Reddy. We do have to apologize all of you for not making you able to talk. I mean, it's just, we have got so many attendees and we just did not want everybody to talk at the same time. So we hosted this as an event and not like a meeting. So we do apologize for that, but we'll be happy to take your questions after Dr. Reddy's talk. Thank you.
Thank you so much, Dr. Raj, Dr. Reddy. Thank you so much. Before Dr. Reddy presents his seminar, I would like to mention again to our viewers that you may type your questions for Dr. Reddy in the Q&A box in the WebEx window. Please put your name and affiliation as well at the end of your question, so Dr. Reddy and I will know who is asking the question. I will then read the questions for Dr. Reddy to answer, and he'll try his best to answer as many questions as is possible. So it's his birthday, so cut him some slack. And yeah, so without further ado, let's welcome Dr. Reddy, the birthday boy, who will be giving his seminar titled Teaching, Research and Service, Passions of My Life. Dr. Reddy, the floor is yours.
Thank you, Prakash. So let me begin by greeting everyone. I don't see your faces, but I'm very, very grateful to you for taking the time to log in and listen to me. In fact, I won't be here without the friendship, support, help over the years of many of my students, colleagues, many collaborators around the globe. So I know that only a fraction of them would be listening to me, but I still think of them on my birthday and occasionally, depending on what I'm thinking. But I'm really very, very grateful to all of you. Thank you for logging in to listen to me. So let me begin with the first slide is to just remind you that there was a plan to host a conference in College Station yesterday, today, and tomorrow. That was the original dates. But because of the COVID-19, it is being postponed. Now it would be held during the 15th to 18th. Actual dates of conference are 16, 17, and 18 of March 2021. So please take time to come and greet me in person if possible. I hope many of you would be able to come. If you have any questions, you can log on to the website here. You can see at the bottom. And the conference chairs are Professor Arun Srinivasa and Professor Thomas Lacey, Jr. And I would just encourage you, I know many of you either not able to come or because of visa issues, there is a delay in processing all of that. So we like to see as many as possible, especially from the Americas, South, North, of course, USA. And let me go on to my actual presentation. So you can see, before I begin, I might say a few words here in the form of a disclaimer, because I don't want anybody to think I'm speaking on behalf of Texas A&M, where I'm an employee, but this is a standard disclaimer. But my presentation is really a combination of personal and professional perspectives, and it includes some advice to junior colleagues. The word junior is really nothing to do with age. It's just a question of not having as much experience with things. And of course, my colleagues with the same level of experience and wisdom, please forgive me. I'm not lecturing. It is really remarks and views on some of the professional matters which I believe would be of help. And of course, some elements of my presentation are useful to academic colleagues, but they are in general relevant to anybody, whether they are at the university or outside the university. And my own students, they're all over the place. They're equally distributed in academics as well as in industry. And I'm very proud of them. And I can't say enough about it because I'm here because of them. So at the end of the presentation, I will be available, as Prakash mentioned to you, that I'll take any questions. That includes criticism. And of course, criticism is at this age and time, for me, is not a big deal. I'll take it. And as much as possible, I'll try to address the comments. So my journey in mechanics is really started with my work at University of Alabama under Professor Oden's guidance. So I have acquired a lot of ideas, not only technical, but by teaching, learned things that I wanted to share. So the article that I wrote as a guest editorial is published in Journal of Applied Mechanics on the occasion of my receiving 2019 Timoshenko Medal. So those who are interested can either visit the website of Journal of Applied Mechanics or even the website of our Center of Innovation in Mechanics for Design and Manufacturing, where you saw the link to this presentation. So the paper is also available there. So with that, let me talk about a few words about myself. First, I was born into a really lower middle income farming family. And my father was an agriculture farmer. And so I was one of actually the only one at that time going beyond high school to college. But I had a very, very good family bringing up in the way of being responsible, work hard. So those elements definitely helped me quite a bit in the years later. And unfortunately, my mother died of cancer when I was 11 years old. And I don't really, other than her image in my heart and my head, I don't have a single picture of her. But you know, I know she would have been very proud to see me, what I have been and what I've been doing, especially as a human being. So the course that I went through at that time was a 5-year integrated course. I took courses that a mechanical engineer does not take, including surveying, blacksmith, carpentry, whatnot, everything, because there are 5 years. So we were able to learn a lot of things by hand and, in theory as well. Every course also had a lab, which is not the case these days. Then in 1969, January, I came to United States, as I mentioned to you earlier. So then I joined in 1970 Professor Arun for PhD. And then my wife joined me during that time. That was a year later in Huntsville, Alabama. So then I graduated in 1974. So continuing with my professional journey, I worked for a very short period with Lockheed Missiles and Space Company in Huntsville, Alabama, and then joined the University of Oklahoma. Actually, within a month or so after I joined Lockheed, I was offered a position as an assistant professor by Professor C.W. Burt, who introduced me to the subject of composite materials, for which I'm very grateful to him. He's no longer, but I always feel these people, came into my life and I benefited enormously. And I really took off doing things that brought me a great deal of visibility in the area of composite materials, especially with shear deformation theories, which I will say a few words later. So then I moved to Virginia Tech in 1980, and in 1992, I'm here. So I'm still kicking, and it is a very, very good experience that, I lived in one place 30 years, and that is this, College Station. I never lived in India 30 years, not in one place anywhere in the United States. So it has been a long time in College Station, and I'm very fortunate to have a teacher and a mentor in Professor Arun, who provided the right initial conditions. And then I found the passion for teaching and research, which I didn't plan when I came to United States. That was not a plan, but it happened very naturally. And along the way, people helped me to form my own boundary conditions. So that is how I'm here. And of course, the life is both boundary and initial value problem. So now I want to say a few words about teaching. So the most important thing that comes to my mind when I say these words is really I learned I learned a lot by teaching because I have to stand in front of the students and say things with a convincing way, with confidence, explain. And that requires you to know the subject. You cannot just wave hands in the air. So that is how I really learned, because I had to study a lot. The things that I was familiar with, now I had to question myself, why so? You talk about Euler Bernoulli beam theory. So why those restrictions? What are the implications of these restrictions? So that if a student asks, you would be standing there explaining with confidence, authority. So this is really a wonderful experience being a teacher, because I took it very seriously and because I wanted to explain things the way I understood. And then I also enjoyed working with young people in research, because this is everywhere I've been, it is a research institute, in the sense that it is not only teaching, but we are required to do research. And that was very consistent with the way I went through in my education. So I had really, I tell people, when, especially young people, it is not just you. It is always the students. You have to be really lucky, fortunate to have students who are very good, hardworking, and motivated. With a little help, they should be able to do. And I had those things in my students. I was very, very fortunate to have these people, and the working with them. And young people always bring energy to you and excitement that drives you. And there is no other profession in the world. I mean, people might think of priestly class or others, but I think the teaching profession at all levels, I'm not talking about just college, starting from kindergarten, they are the most important people who have the ability to mold both as a person and their character ability. Of course, we cannot change completely, but we have the opportunity to mold these young people, and in building their professional future and their character as well. So this is why I feel a teaching profession is not only just a noble, but it practically has the ability to mold people to become good citizens of the society. So when one thinks of it as a job, but it is really a responsibility. I'm talking about teachers should take it as a major responsibility to work with these students and help them. So you must have passion for it, passion for learning, and passion for communicating your understanding of subjects in a fashion the student can comprehend. So teachers must put really selfless efforts to make their own hard-earned knowledge and expertise accessible to motivated students. And of course, you can only do so much. You can take the horse to the water, but the horse has to drink. So that is the way I see. You have to motivate, you make them excited, but they have to have their own initiative to learn. But we must do our job. We must derive personal reward, not from demonstrating to students that we are experts, but from being able to explain complex ideas in a way that they can comprehend and ultimately master these ideas and utilize them in their professional careers, whether they are in industry or in academia. Of course, main things that I feel in teaching is clarity and physical insight of explanations that we give them, especially most difficult topics. And I also believe you have to go through relevant examples to illustrate, because saying these very complicated ideas, without examples, many people don't see it, especially students of engineering. Mathematics is a different thing. You can come up with an abstract idea and then you use some example to illustrate how they are special cases. But we have to build. I like building approach. That means you go from simple ideas to more complex ideas. in making the students to follow you. If you go suddenly to very complicated idea, they may not follow. So along the way, you should never be shy of mathematical rigor, because mathematics is the language of engineers. You should never ever think mathematics is for its own sake. I mean, especially I'm talking about engineers. They must, have enough mathematical rigor in everything they study, because they tell you, they explain you what is happening, at least qualitatively. So it is very important to me as a teacher to follow such a approach where mathematics was a integral part of my teachings. So especially for young people out there, and I'm sure that many of you, met me one way or the other, and my advice to you is to tell you that every time you teach a course, you should prepare. Even if you taught it 10 times, night before and few minutes before going to the class, you must review in your own head or on a sheet of paper what you're going to cover. This is very important. You don't walk into the class while cleaning the board, you say, oh, what I'm going to do today. And that will show up not performing well in the class. So you must prepare every time. And you relate what you teach. I mean, topics that you are going to teach to common sense thinking and to material covered in the previous courses that are considered to be prerequisites. So I also did this both in terms of classroom teaching and also books. Introduce fresh ideas from your own personal research. I think it is always good because it excites. They may not find it in the textbook, but you say things, you relate to it. Something you were working on your research, if it is relevant, you should bring that into the classroom. Be open and fair to your evaluations in your evaluation of assignments or tests, because this is something I think we tend to, as human beings, always, somebody who comes and sees you more often tend to think that student is your favorite. Well, it's not necessarily, because they didn't understand enough, they are seeking help. So don't develop this kind of partiality just because you happen to see them or talk to them. So you have to evaluate what you see on the papers, whether assignment or exam papers. Don't think beyond that. Okay? You can encourage them in any way you want, especially those who are not performing well. Give enough encouragement. You can offer more help. And also allow sufficient time for questions and office visits. And this is very important, especially if you're teaching large sections that have many, many students. So if many of them may be shy or feel that they cannot ask or feel uncomfortable to ask in the group. So you have to provide them opportunity through office visits. And also, it's one of the things that young faculty tend to, try to help, or may think that their teaching evaluations will be better if they give them makeups. I think that's wrong. You never allow, you should avoid and discourage giving any makeup exams. And sometimes they even ask after the final exam, oh, how do I make up my grade? I say, no, sorry, it's too late, because even who got a B wants to make up to get an A. So there is no end to it, and it is not fair. So giving too much help also is not a good thing, because you make them parasites. They will not have that help once they leave this place. So you should know how much help you should give. And it should be always, if they are really drowning and they are 6 feet away from you, you only throw 5 feet rope, because they have to swim or move toward that rope 1 yard. That means that shows they're trying. So you must not give too much help and feeling that, oh, I'm helping, but you're not helping, because they become used to it, and that help will not come once they leave this place. Now, the other responsibility, especially in university, and this is true even in an industry, because senior members can mentor younger people, junior members. So especially in the context of university environment, a teacher must be a mentor to his students, postdocs, and even junior faculty. So this is a very important responsibility people should take seriously. So the focus of mentorship is not just to help. Helping means, tell them where to get money or how to write a paper, but really develop that person and during her or his career. So you have to be there in anything, everything that they have questions. Sometimes it may be even personal questions, non-related to university, but that kind of confidence they have to have in you. And that comes by having the right kind of chemistry developed between you and the mentees. So a mentor must commit in a caring way. This involves taking part in the learning process side by side with students, postdocs, and colleagues, especially those who are in industry. They have to do the same kind of thing, because mentoring is really a very important aspect of life. No matter what you do, I'm not saying just as a teacher, but any job you do, helping younger people or juniors to learn the art and skills of that profession and being taught things about the life. Because see, everything is connected ultimately to life, because we have to live in this world, take care of the family, take care of the job, take care of the society we live in. So all of these are at our heart, one day or the other. And also you must treat students, postdocs, just because they are not same level as you should not treat them something that they're, not up to you. So that is not the way. You have to treat them like you would treat your colleague, fellow, professional. And you also teach your students and colleagues the art and skills of teaching, research, proposal writing, oral communication, and interpersonal skills. All of these may look like more related to academics, but this is true even in industry, especially in high-tech industry. And now I come to research, and there are few professional highlights, and I'm not going to talk about this. Is probably will take forever, several lectures. So I mentioned in answer to a question that Dr. Raj Kota asked me during graduate school, what was, how did I get into research? So this is the very first thing I did in my research career: primal dual variational principles and mixed finite element approximations. These are the two topics of my dissertation, which led to several journal papers, but also two books that I co-authored with Professor Arun. When I joined Lockheed, I was given a project. Even though I was there 6 months, I worked on hypervelocity impact project, and they gave me developing a 3D finite element code to study hypervelocity impact. Since I got the job within a month at University of Oklahoma, I thought of leaving, but then I thought, well, this is an opportunity to show that I can do it. So I postponed. I called Charlie Bird. I said, I cannot come now, because they asked me to come in September of 74, and I was at Lockheed at that time. I told him I will come in January of 75, which is spring semester. He said, no, we will wait, no problem. You can take your time. So that gave me an opportunity to learn something by doing. So this is the time I really became a good programmer. Because before that, I was doing, programming to get numerical results for simple things. But once I got into the company, I was really under the gun, so to speak, to develop this code. And this was sponsored by NASA Glenn. Glenn, of course, was not the name at that time, Cleveland. So I was able to complete the project to a good extent, then pass on to whoever came on board. So then when I joined University of Oklahoma, I worked with two different groups. One is in geology, geophysics, another in geophysical fluid dynamics. I didn't put it here, but those two also totally outside of my regular training. But I acquired this fundamental understanding of mechanics problems and computational tools. Those two are most powerful. You can really attack anything and everything. You can study them, new phenomena, formulate new problems, and really develop computational schemes to study them. So then with Professor Charlie Bird, I worked on composite materials, especially bimodular materials, materials that exhibit different moduli in tension and compression. And this is very typical of tires that, fiber reinforced tires, Kevlar, reinforced fibers in the rubber. They do exhibit different behavior in compression and tension. So this is even though each of the modulus is considered to be linear, means Hooke's law is applicable, but it is different in tension and compression. So it makes mathematically a nonlinear problem because you don't know the state of stress ahead of time at a given point. So that was, so it led to several papers. And then this was I think the most celebrated topic of my life. And by reading the papers by other people, including Reisner, Mindlin, and so on, I learned that there are some limitations of the theories that are there. So especially as applied to composites, because laminated composites are weak in transverse direction, very strong in the plane because of fibers. So I had to think of how to come up with a theory that accounts for the transverse shear stresses which are responsible for failures. So this third order shear deformation theory and then layer-wise theories were developed during that period. And also because of, again, my background being very general, I was able to work in fluid mechanics, and that is the same thing I did with geological and geophysical fluid dynamics. So I worked on penalty finite element models of fluid flow. In fact, I don't say it here, but I also used penalty finite element formulation to explain how Mindlin plate theory, first order shear deformation theory, can be derived from the classical plate theory. And I identified the penalty parameters as shear modulus and shear correction factor. And so that is another highlight of that work. Then I worked on, I traveled to Singapore during 1998 to 2006, and I met Professor Wang there. And so this is another topic that I worked where we developed algebraic relationships between the solutions of classical and higher order shear deformation theories. So algebraic relations means all you need to do is have classical solutions. Many of them are available in the books. Then you can immediately obtain the shear deformation solutions for the corresponding problem. So, well, I continued my interest from the third order shear deformation theory till today. I've been working on refined and robust shell finite elements, and I had the fortune of having several people in the last, I would say 10, 15 years who worked on this topic with me, my PhD students. And I'm not naming them, but for the fear of not naming everyone who worked with me on other topics. But again, I'm very fortunate to have these students worked on them. Then I also worked on least squares finite elements for fluid flows and also structural mechanics. This also continues now, and latest PhD student who worked on with me on 3D fluid flows for non-Newtonian and generalized fluids, she used least squares finite elements. And the latest passion or interest is non-classical continuum theories for damage, fracture, and architectural materials. So I won't go into any of these, but I will show some highlights in a few minutes. So, but all of these topics have the following themes common. Everywhere I will have variational concepts, weak forms, and Ritz-Galerkin methods, and then shear deformation theories of beams, plates, and shells. No matter whether I'm working with non-classical or least squares, refined, all of them. And of course, computational approaches. And finally, applied continuum mechanics. So which is the mother of all, because without which I won't be able to say and state problems in a meaningful way. I won't say exact way because there is no such thing as exact. So continuing with this, and many of the books that I'm showing here are single authored, and except for the last two, but these are all related to those themes. So I think, again, as I said before, all of them except for this first one came from teaching. So the sole purpose of writing these books, I was never thinking of impressing on anybody. In fact, many of you know that people don't really, especially in the administration, don't care if you're writing a book or not. They want your money, papers, and so on. This is the last thing. And when you show that you have authored a book, they pat on your back. Oh, that's good, congratulations. But that's it. But my passion, interest to write these books is to facilitate learning and provide tools, and also, report the latest advances for the benefit of the readers. So that was the main reason, not because I wanted to get a raise or impress somebody. So I tried to include, as I just mentioned, relevant research ideas into my books, especially later editions of the same books. Every time I do a new edition, I bring my latest research into it. So I will say a few words again about my view on mechanics and modeling. There are two words, mechanics and modeling. So the first thing is I want to say that everything that we do, engineers, applied scientists, whoever it is here, we model things. Model means try to represent, characterize things that are in nature, or we use the nature as example to build, manufacture things, but we have to understand them before we go to the manufacturing or design. So modeling is a very important and necessary step in engineering process. Nothing can be engineered without starting with a model of it. So modeling requires mathematical and computational models. So there are two, the word model again came because mathematical model means it is a set of algebraic, differential, or integral equations, or combination thereof, depending upon a specially constitutive behavior. And then we need computational tools because these equations are highly complicated, especially if they are nonlinear, and if they are posed on multi dimensions, account for multiple processes, sometimes called multiphysics, but the same physics that accounts for many things that we care about. So, and then without the computational models, we won't be able to see the intricate couplings and effects of certain nonlinearities. So and even linear problems, if they are complicated in the sense that you are working with geometries that are not simple, it's not possible to find analytical solutions. So computational models are necessary these days. And of course, I'm not saying that you don't need experiments. You need three things. You need experiments, you need theoretical models, meaning mathematical model, and you need computational models. I said these are the three important legs of a stool on which we conduct our professional works. So there is no complete mathematical model of anything that we do. Okay? So we are only, I mean, this includes continuum mechanics or elasticity or fluid mechanics, any equations that you study in dynamics and controls. All of these are mathematical models. Models to the extent we understand or our ancestors, forefathers, are able to tell us, and we stand on their shoulders to see further. So that's exactly what we are doing. So it is really to improve what we already know because of, again, these people who have helped us see that. So we are, by doing research, we are looking for how to improve them, how to make it better, both in terms of mathematical model as well as computational way to determine the solutions. So only two things matter in engineering. I mean, this is a broad overview of the field of engineering, whether you are in industry or in academia. Of course, especially industry, knowing the probability of failure of the system that you are working with, trying to develop or build. Because that is what we need to know when it is going to fail so that we are prepared to replace or repair. And second, equally important is make sure that we don't overly, expensive. And these two don't go together. So there is, of course, a lot goes into this knowing the probability of failure. In fact, all of the things that we do, whether you are in industry or in academia, is to focus so much on finding the probability of failure, the strength and failure of the things that we develop. And at some point along the chain of command, the designer and manufacturers will pay attention to the cost. And the cost is not always goes with the so-called functionality. Now, you want the reliability of function of the product or system, it usually costs more. And depending upon what that component is, we may make the judgment. If it is a medical prosthetics, we know that we have to make them as reliable, functionally speaking, as possible. So we tend to spend more money to make it more reliable. Whereas if it is something that you're paving a road or something, we say, well, we will repair it when it gets worse. So the cost probably will get secondary look. We don't, when I say secondary look, that cost is not, a major issue that you try to make it cheaper, but the human lives are not at stake in those kinds of situations. Okay, so then another comment related to the computational methods. We talk about discrete methods in the form of finite differences, that is the age-old topic. And then, of course, finite elements came, boundary elements came, then meshless methods came, and finite volume techniques, and so on. So this is the meshless methods for the same two-dimensional object. And then there is the finite volume. So what you see when you look at these three pictures, no matter how you mesh it, you see something common are those points. So what are we trying to do? We are trying to convert the differential equations or integral equations or combination into algebraic relations using the concepts of discretization were specific to that method. But at the end, what we are getting is AX equal to B, where A is the matrix of known things, and X is the column vector of unknowns, and B is the column vector of knowns. But when I said X and B known, it's not quite right, because before you apply the boundary conditions, some elements of X and some elements of B would be unknown. So what we are doing is, at the end, we are trying to develop relationships between the duality pairs. And these relationships are algebraic. And duality pairs I'm referring to are cause and effect, like force and displacement. temperature and heat. And similarly, velocity and pressure or forces again. So these are duality pairs. And when we talk of boundary conditions, the word boundary is not really important because it's not just the boundary line, but at every point in the system or mesh, we have to know one or the other. You cannot say that I don't know the other one. Well, only if you know one of them, yes. But if we say I don't know either one, that means you don't know. There is something you must know. So you will quiz yourself. What is that I'm missing here? So at the most, you should know a relationship between the cause and effect. If not one of them is known, you must at least know how those two are related. Like if you have a spring-loaded cantilever beam, then the shear force must be related to the displacement there. You don't know either one of them. So that is how the duality pairs work. So the message that I'm trying to give here, not only everything that we study is not exact, but when we discretize, we make assumptions in discretization, then we must also realize at the end of the day, we are really trying to solve for the unknowns, which are duality pairs. Some of the cause things, some of them are effect things. So, and I already said something about boundary condition. So now I want to say a little bit about composites, but here again, I won't take too much time. So this is really the most, I guess, visible work that I have done over the years, and the third order shear deformation theory, and that was published in 1984. I think it's nearing 4,000 citations. And the layer-wise theory that is also known in the literature. So one example of the higher order theory is the theory that we developed in recent years, is the thickness stretch shell theory. That means when a structure is subject to large deformation, think of an internally pressurized cylinder. And you know it's going to bulge out, become larger diameter shell, right? So then how is it going to be larger from that same size, and it's becoming larger? Means material has to flow to make up this larger cylinder, larger in diameter. So that means the material has to flow from thickness into the surface. That means thickness has to get smaller. But you know, all of the existing theories until recently only account for inextensibility concept. Means through thickness, nothing changes. That means thickness of the deformed, undeformed shell is the same. And you know this cannot be true. But most important part that I want to emphasize here is not the question of thickness being changed so much. Of course, it does change, especially for large deformation. But saying that it doesn't change makes the mathematical model overly stiff, because you made the thickness rigid in a way. Nothing can happen in the thickness direction. So that is bringing artificial stiffening effect into the mathematical model as well as computational model. So to overcome that, you should say, let it go. Okay, don't put that restriction. And that's what we have done. So if you take this cylinder and internally pressurize, by the way, this is one of the things that may happen. I knew, although I put it there, but so yeah, don't worry about it. This is the cylinder that when it expands, you will see the thickness stretch, and I'm going to show you the thickness stretch. See, this is part of the ratio of the thickness change divided by the original thickness along the length of the cylinder. So you can see within the vicinity of the boundary, because we fix the ends, and so it will start thinning, and then it will essentially remain constant as shown here. So that is the figure I wanted to show you. And because of that theory, we were able to study internally pressurized cylinder and compare the results with abacus. Of course, ANSYS, abacus both have shell elements as well as 3D elements. So look at this, circle and the square. Those are the two shell elements and they go like that. So they are going away from three-dimensional solution, which is the dark circle and the diamond, both of them coming from ANSYS abacus 3D elements. And our shell theory with the stretch included is doing very, very good all the way up to here. So then it doesn't do as good in the large, loads because, still it's a shell theory, not a 3D. So, but, it's remarkable. So, see, I could have, just to fool you, I could have cut it off here, but that was not the intention. I want to tell you the full story that we have still room to improve. But improvement may not come because if you can constrain your model to be only 2D. And that's what we are doing in shell theories. So, but it really remarkably came so close. So then you might say, oh, why don't we use 3D elements? Well, if you use 3D elements, it's 50,000 degrees of freedom for that simple problem. Whereas it only takes 2,000 degrees of freedom with 7 parameter and 3,500 for 12 parameter. And our 7 parameter already does a very good job. So you can see computationally very efficient to use shell elements. And the last topic of this discussion really related to non-local mechanics. And there are several things we can talk about architecture materials. But this non-locality is a phrase we use to mean that we can model anything and everything in nature by bringing certain parameters that globally represent features that are occurring at micro level. Or it could be macro level if it is mega structure. Okay, so think of a ship, and ship has all kinds of elements, including the deck, and deck is made of one of these, for example, right? And it has all these ligaments. So if you start putting all of them into your finite element model, trillions of degrees of freedom, which is not doable. So you will find way to represent this deck as just a single layer plate, but account for all these architectural details through some kind of length scales. So that is what I mean by non-local. It's not always material length scales. It could be structural length scales. Okay. So we have done something like that. For example, here is a simple plate with the architecture is shown here. It is the iWeb core. And if you try to model this using single layer theory, you will get decent results, by the way. It's not that you don't. But if you really look at very closely, especially the stress state under the line load, you will not get very good results. So what we do is we do locally 3D element, 3D finite element analysis, and then connect the information from the 3D finite elements to a plate theory. So this is the micropolar plate theory where we allow the point rotations. So which amounts to saying this web here, in a global single layer theory, it is lost, right? Because when we convert this 3D to 2D, it is homogenized. But by bringing these rotations, we are able to say how this web is going to rotate, okay, at a point-wise. So point-wise rotations is what micropolar plate theory is. So how do we connect the 3D to this 2D? And that is the challenge. We go through energy equivalence, okay? So we construct the strain energy for this, and the D denotes the degrees of freedom, finite element degrees of freedom. Then we construct the finite element model of this micropolar plate theory, where stress resultants are related to the strains through the ADGH, that is where the stiffnesses are. And this is where the 3D effects are accounted. So the developing this equation is the crucial. And that is done through a 3D to 2D connection, by energy equivalence. So I just want to show you the result under line load, and especially if you look at from the edge to edge, and the 2D micropolar theory is here and 3D finite elements is right there. So you cannot see the difference between the two, whereas the conventional results are way off here at that location. So that is the benefit of bringing non-locality through ingenious way into the simple global analysis. And the last related to the non-local mechanics is Graphia. It is the name given with my colleagues, of course, who is hosting this show here, Arun, Srinivasa, and Prakash, Thamburaja. So graph-based finite element analysis, it piggybacks on the traditional finite elements. There is no new finite elements here, but we bring non-locality thinking into the, identifying the damage and fraction. So this is an example of a material, and finite element simulations using our Graphia does. By the way, both of them on left and right are experimental, and the one in the middle is the results predicted by Graphia. And it is also done with, by the way, we have UMAT into Abacus. That means Graphia can be used in conjunction with any commercial code. And we also can use, of course, XFEM like codes from same commercial code. And we found that the XFEM doesn't do the job. It did not predict what we were able to predict for this problem. So the element failure method coupled with the non-local fracture criterion is able to simulate the mixed mode propagation. So I will close this by showing you one more example here. So this is just to see the mixed mode fracture. And if you fix here and push it here, and the damage will start here and fracture initiates. I'm only hoping it will work. Okay, I think it's working. So you can see how the fracture. And by the way, if you're thinking of the diffuse zone is wide, it is related to the fracture criterion. You can make it sharp if you want, but in reality, the zone is indeed, it can be more diffuse than you think. And of course, it is property of the material also. So I will just stop my research discussion and just tell you that it is better to be roughly right than precisely wrong. So again, I'm saying the same thing, that everything that we do, we are modeling, and there is nothing exact. But you make sure, with the help of the mechanics concepts or the topics of your subject, you must know what is right and wrong. And that comes not by looking at the equations, having in-depth understanding of the equations. So you must pay attention to the subjects that you study when you are a student. And then when you are a researcher, keep learning. So my advice to young people is to keep the long-term research objectives in mind. Don't jump around and publish here and there, and you never will be known for anything. You may have a lot of papers, but people must, when they see you, they know what you work in. Or when they read a paper on a topic, then they think of you because you're one of the leading people. So you must really keep this long-term research objective in mind. You should stay with this topic long enough. I'm not saying you should work only with one topic, but they should be finitely few. Focus in the specific area that is not saturated. And this is not easy one to do because a lot of young people ask this question, how do I identify a topic for me to work? So one of the things is, of course, you have to develop some kind of passion for that topic, and also see if there are too many people working. And so nano, bio, of course, those are loaded areas, but then you can find some subtopic of those areas, focus on it, and become a leader in that area. So conduct research to publish and seek sponsorship. This is the game that we have to play. And so I'm not going to sound like a saint, that you should only, try to understand and investigate, but not publish. That's not good. You must share your findings. And the academic culture in most of the places, especially in the United States, is to have sponsorship, without which you cannot support your students, you cannot buy equipment, you cannot travel, you cannot really support postdocs. So all of that is necessary. So, but it should not be an end in itself. It is a means to do something. Okay, so there are people who get lots of money, and probably they do something with the money, but it may not end up in doing things that people consider important. So be careful about this. So the other thing I say, especially young people, if you don't have that in your bag, you must learn, you must practice. Organize your time around teaching and service to do research. Because research is not a scheduled event unless you want it, right? So it is a flexible scheduled thing. Whereas teaching and service, usually committee meetings, all of these are scheduled. So you have to show up to do those two things, but research is not. So research should be a fluid. It should go around these two things every minute you get. So you should have that ability to switch back gears, one to the other. And this doesn't come just by me telling you, you have to practice it, okay? So it is the impact, not the numbers, that ultimately you have to regard. And another thing, that it is better to be roughly right than precisely wrong. So your research should always pay attention to this. And also this is, I think, James Bryant said that science advances not by accumulation of new facts, but by the continuous development of new concepts. The concepts are more important. Finding facts is okay, but you have to come up with new concepts, new models. Okay. Now, the last part of my talk is service to the profession. So this, a lot of times people take it very lightly. But any measure of success of any person or any accomplishment must include giving back to the community, giving back to whatever profession you are in. So if you don't give, it is lost. Whether it's the knowledge or the mentorship or any kind of evaluating other people, all of this you must do, because you have been taxing people to do your things, right? When you publish a paper, somebody is reviewing, one or two people, at least two, right? So you have to review two papers. So that is the way you have to think. Serving the profession is an obligation and also a responsibility. So you must take it seriously. So I won't take too much time to talk about myself, but I've done a lot of it. I continue to do that, especially these days, not only in the university departmental committees, but I still continue to be an evaluator, supporter of colleagues all over the world for tenure, promotion, writing support letters for honors, awards, because I think I owe them, because people did that for me. And I only want to do a greater than one factor of multiplication, because that's the only way I feel good. So some ways that you can serve the profession is review the journal manuscripts. That is always good, by the way. Proposing reviews, and also serve on professional technical committees, whether it's the state, national, international, organize sessions, symposia, and of course, membership on editorial boards. They don't come just because you want to be on it. You have to earn it. It takes time. Okay, so that will come only if you do other things right. And the benefits are tremendous, because it will give you this connectivity. And when people send letters to them to evaluate you, they know you because they work with you, or they came across your work, or you met them at a conference, you organized a symposium where there were presenters. All of these come back to help you. So we must also think of serving the society. This, I think, many of us do in a discreet way here and there, but I think especially connecting to local social clubs or high schools or elementary schools in terms of science projects, or even as a coach for soccer teams, any of those. I think we must pay attention to this. It cannot be, just think of, oh, that is waste of time, because there is what you think is a waste of time is a constructive time for others. So you should never judge only what is in for me. Okay, so manage your time between different responsibilities in life, family, job, and profession. Of course, it may be easier than done, but we can do it. It is not, I'm not saying it should be 1/3. And different days, different ways. Some days it may be 100% family. And some days, lot of days, 100% job or profession. Okay. So be passionate about everything that you do, teaching, research, and service too. If you don't show interest and you go to the meetings, only talk and put things there and make other people time wasted because you just bring all kinds of questions but no answers. That's not the way we work. We must identify problems and also find solutions to problems. And first and foremost important responsibility of a faculty member, especially, I'm addressing the colleagues in the universities, to impart knowledge. The students are the most important, people that we have. They are both our customers and our products. We should take pride in them. We should facilitate their learning. And it is almost more satisfying to work on problems that may have applications to real world problems. So this is connected to research. And so what I'm saying is, if you only continue to extend your dissertation to one more paper, well, I think it is time that you try to find out what really the companies are looking for, or our research labs, government labs are looking. What are the technical problems or challenges they are facing? Whether they're for the societal needs or defense needs, you need to find out. And I think it is important to work on those problems that have applications to real world, ultimately helping the humanity. Industrial relevance also helps for you to get funding much easier than just some academic topic that seems to be very interesting. We can publish, but getting sponsorship is not easy. So I will probably say a few words about the pressure that young people feel these days to publish. I think you should, there is always a sequence. It's like first you need learn to crawl, then you slowly walk, and then learn to run. So you must not pay too much attention to the impact factor, citations, all that. But first you should publish. And sometimes it has a negative impact because you are under pressure and you are publishing left and right without paying attention to the quality of your contribution. So you must make sure that the citations and impact factors these days are there being gamed. The editors of the journals are people who want to get high citations. They are playing games. Not everybody, but there are people who are doing that. So I don't think you should really pay so much attention to lose your sleep on it. You must not keep that as your goal. You must think of what is that I'm doing, how is it is going to impact. Okay, so you should not worry about that. So how it is going to make a difference from ultimate utility of your work. And again, for academic people, tenure is earned when you do your job of teaching, research, and service as good as it possible, splendidly as you can. Okay, so if you only worry about tenure and promotion, you start checking boxes. What are needed for earning tenure? Once that is over, then again, next promotion. How do I get that promotion? You are only checking boxes, and that is not good. You must do your job and derive satisfaction, happiness, and things will take care of themselves. It happened to me, and it will happen to every one of you. I'm nothing special. So you must serve your institution, profession, and community with feeling of responsibility and without asking what is in for me. So satisfaction lies in the effort, not in the attainment. Full effort is full victory. This is what Mahatma Gandhi said. But I also say everything anybody said is already been said by others, I'm sure, in other ways, other forms. So it's not that Mahatma Gandhi is the first one, but you must take the wit and wisdom in this statement. Okay, so it is time to give my last words. The most common question people ask me is, how did you write so many books and papers? So it's a good, that question was not asked in that form by Dr. Raj Kota, but really I already answered it partially, but I always joke saying that I have a twin brother who works in the basement for me. Okay, well, of course, Texas has no basements. So seriously, I have benefited enormously. I mean, I really mean it, by working with my students, postdocs, colleagues across the world, and continue to do that. In fact, my productivity in the last 5 years is even up. I mean, you can look at it. Look at, any place that these are available. I'm sure they are everywhere, but I will not name each and every one of them. And especially, there won't be any time, and there are so many, and I won't remember every one of them at the moment. So what I want to do is to dedicate this lecture to them. This is to all my students and collaborators all over the world. And some of you are listening to me. It is really dedicated to you. I really thank you wholeheartedly for being a collaborator in many ways. Not just you have to write a paper with me, but even work with me on things of importance. But I'm really grateful to all of you. So I would not be where I am today without the help of all of you. So I'm also grateful to the research support over the years by various agencies. I may have missed some, but there are many, many agencies here, including, of course, the Army Futures Command, Air Force Office of Scientific Research, Army Research Labs, and so on, the NSF, and other private companies. So I'm very, very thankful to them for allowing me to continue with my passions. And I also met and received help many staff members everywhere I've been in the academia, University of Oklahoma, Virginia Tech, and Texas A&M. You wouldn't believe it, in the beginning, all my books were typed by secretaries. That included Virginia Tech especially. Only in recent times, I'm typing myself for my students, but really, they were very kind and helpful throughout my life. So I sincerely thank them. And I don't think any of them are logged in, but if they are, sincere thanks to them. The idea and encouragement to present this webinar came from Arun, Professor Srinivasa. He coordinated the event with Drs. Prakash, Thamburaja, and Raj Kota. And I thank them for their efforts, and they are still here. And especially the artistic rendering of my books and medals by Raj Kota, they really challenged my presentation. How can I live up to this beautiful preparation, website or webinar invitation that Raj created? Thank you, Raj. So, I'm celebrating this 57 transpose birthday. Actually, I don't feel 75, okay? And not only that, in fact, I don't know if my father gave the right date of birth, because when he walked me to the school to join, and they would ask this question, what is the date of birth? And typical male, or a parent, or father rather, will scratch his head and then try to remember when I was born. Oh, maybe on a full moon day or 5 days after full moon. So they will do some rough calculation and give the date of birth. I mean, I'm talking about people of my age in rural India, right? So it could be I may be a year off this way or that way. And hopefully this way means I'm younger than people think. Or I think some people already said that I look younger, but anyway, I'm not boasting about that. But most important thing, every day I get up and then right after taking a shower and having a tea or something, I just walk into my office and start working on where I left off. So it's always I'm looking forward, only because I have this interest and passion for what I do. So along the way, that one person, I mean, there are many I dedicated this talk to, but one person constant in all of these is my wife. She's a major and a critical contributor. I never have to worry about anything. I mean, I just told you that get up and take shower and have tea, and tea is prepared by my wife. I'm not making my tea myself. I'm not proud of it, but I'm telling you the fact. I'm eternally grateful to her for her love and the amount of dedication. I also want to thank many relatives, friends, and colleagues who are not professionally connected, but they are all contributed to my life. And finally, thank you all for your interest in my talk. This chat is really, it's not a lecture. I want to refrain from using that word because I had really chatted with you, expressed my views, made some remarks, but you are kind enough to log in and listen to me. Thank you. So here is my 3 grandchildren. So I used to think they are stress relievers when they were younger than this. And now, of course, they're also giving me stress, running around, giving me, questions. So, but anyway, still I enjoy them. So I'm going to look forward to seeing them as soon as possible. And I really looking forward to get rid of this virus and from our lives. And I hope all of you are praying for that. Okay, so I'm here. Prakash.
Thank you very much, Dr. Reddy, for a very thoroughly engaging seminar. I'm sure the advice that you've shared today will really help us in having a long and fruitful career in teaching, research, and service to our community. Yeah? So we'd be happy to have the same passion that you have, for years to come. Thank you so much again, for a wonderful lecture. So are you ready for some question and answers from our audience?
Yes, I am ready. I don't even have to go to washroom.
Oh, okay. Thank you so much. Okay.
Before we start with the question and answer, I just want to add, provide my sincere thanks to Dr. Reddy. It's not only teaching service, it's not only the 3 main elements, but you brought a big laughter for the group for sure with your presentation. I'm sure everybody might be cringing that they did not have the microphone in their hand to laugh about it. I'm sure they all enjoyed the presentation, and we wish we had the conference now and everything, all of this happened in live, but it's not too late. We'll have the conference happening in March, so we expect you to see all of you back by then. Thank you, Dr. Reddy.
Thank you.
Over to you, Prakash.
Thank you, Raj. Okay, Dr. Reddy, so there are a few questions here. So I will try my best to ask and to be faithful as the questions. I have to do a lot of paraphrasing. So the first question is from Dr. G. Wang. So there is always a bias against research in university and calling for more emphasis on teaching. What is your comment on this perception?
Bias in more emphasis on teaching.
Yes, bias against research in some universities and calling for more emphasis on teaching.
Okay, I think I'm not sure if I understood the question when he used that word bias. I'm sure people are asking you to be a good teacher, but many times they say this to some extent is a lip service. What I mean by that, they still want you to bring more money and publish more. Okay, I mean, I'm being very direct and critical, but it is teaching and being passionate in teaching is your call. Nobody is going to put passion into you. You cannot go buy it. You have to instill in yourself that you have to see the benefit of teaching, even when you think there is not much coming back to you. But I think it is coming back. You don't realize more, may not be direct, but even as I said, preparing to deliver a lecture in a way that you are making the students understand, that itself will teach you something. And then you must think about how you are able to help them understand, impart the knowledge. So the bias that you're talking about, more nobody other than at certain schools which are more teaching oriented schools who want you to do only teaching or a little bit research but mostly teaching. I think that is not uncommon. So, but I don't think there is any, if you really meant that the bias is toward research more than teaching, yes, I tend to agree, because they really want you to bring money and publish more. And yet times they might say that, oh, you should do good teaching. But really when it comes time to tenure and promote, they look at the research portfolio with more interest than anything else. All they look for is adequate teaching. They don't use adequate research as they want you to do very good research compared to whatever comparisons, references they have. I hope I answered the question.
Thank you, Dr. Reddy. So there are two questions which are somewhat similar. So it's asked by Dr. Moshad and Dr. Narayan Aluru. So how did research change over the last 50 years? And in your opinion, what will research look like 50 years from now?
Oh, this is a very tough question, but I think in the last 50 years, that is almost my lifetime, right? In fact, more than my lifetime. So I can only review my own thing. The way it started, I remember the research was important, but there was not that much focus or push for getting dollars. So now what happened is, I think in the intervening time from 70s till now through 2000, 21st century, the focus has shifted, even at very good universities, to bring a lot of dollars, sponsorship. But I don't want to talk only negatives. There has been a lot of good things happen because we have really come up with a lot of new areas, whether it's bio, nano, and thereof, and because of the computational tools, not because I'm in that area, it has helped people to really take the mathematical models to higher levels. Because see, we are limited by how much we can do with the mathematical model. The mathematical model doesn't allow us to solve it, then we try to neglect the terms that are giving trouble, right? Like nonlinear terms or higher order terms. But now we have the tools. So we can probe, we can investigate the effects of different terms, couplings. So that has happened, and that opened up a lot of areas in terms of investigative research. And we have, more than anybody, engineers have crossed other side of the profession into biology, chemistry, even management, by creating mathematical models and simulating them. So I think, engineers are going to be the real problem solvers of the world, of all kinds, of course, all kinds of engineers. No other profession gives so much to the society, although ordinary person on the street may not see that way, because we are not going to person. A medical doctor will get that kind of appreciation. We may not get it. Everything they are using, whether a car or cell phone, everything came from engineers. And even the doctors, what they use came from engineers. Stethoscope, syringe, anything, right? So scientists by large are the backbone of any society. So to answer Dr. Aluru's question, I think we have come a long way. It looks, and in the future, next 50 years, I think we are going to. One thing that happened, by the way, I didn't say that, the materials also played a big role. So because of the computational mechanics, even materials people can probe how to manipulate the material composition, architectural materials, metamaterials. Okay, so in the coming years, we are going to really get into those. That means we start producing structures that you cannot see with the naked eye, but we create architectural materials that would be very efficient, functionally very good, and also possibly cost less. And all of these are possible because we are making advances both in mathematical model development, largely because computations are driving us. So in the years to come, I think young people should focus on how we can really bring higher order effects, non-locality in different forms, and also biological things that I'm not an expert in that. There is so much. Human body is a mystery. And we don't understand them. In fact, that is one field which is so rich. It will be next 100 generations will take to understand it because we don't have the laws of biology in place. We have laws of physics, which are also valid in biology, but we need more laws. How, if, for example, rubbing your nose is creating sensation in your head and also some chemical is being produced locally, what is the connection between this rubbing to that? So we can only try to model this kind of thing by trying to see through by comparison or imitation. But we don't have exact laws like we do in the form of F equal to ma. So in the next 50 years, we will see a lot more investigative research in non-traditional areas like bio, nano, material science, and biological systems, where we will find more mysteries to be unraveled. And also, one thing we should never forget is to improve our infrastructure. That means in pursuit of new materials, new types of architectural materials, we should never forget that how to repair and make the infrastructure better. So there is enough room there also. So we must pay attention there also.
Thank you, Dr. Reddy. You were mentioning about working in the areas of biology. So this is a related question to that. This was asked by Dr. Tarun Kant. So how was your experience of working in the areas of biology? I understand that two of your students, ex-PhD students, the Unithan brothers, worked in this area. So what is your experience working in this area?
Right. This is an excellent example of Minu and Gino. They came to me, to their brothers, but they came in different 1 year apart, I think. But I didn't have any background or interest at that time in biological systems. But when they came with that interest, I started working with them. Of course, they worked more than I did, and I benefited, but I learned a lot. And so this is, when we say biology, it's really what we did is just a very small thing. In fact, it's only mechanical characterization. What we learned in that one work I can relate to is, we found an experimental result for a biological cell being indented. So there were 3 different groups published results on the force versus deflection by indentation on this. And those 3 were different. So we got curious. What is that? Why is that 3 different? When you think when somebody does experiment, it should be unique. But you should know it's not. especially when it comes to biological systems. How you load it, what is the rate of loading, all of that matters because biological cells are live. If you give enough time, they will put more fibers into their membrane. Okay, so this is what we showed through our modeling by increasing the percentage of actin fibers. We were able to show that we can match any of those three experimental results. So it's a finding saying that the people who have done the experiment, they did not do the experiments in identical conditions. So it's not that they did anything wrong, but the conditions were not the same. So that is the result of this finding. So again, we didn't develop a new mathematical model, but it is really using existing tools. But modeling is very important term here. How do you model actin filaments and the fibers and also the membrane? And so all of this is where your modeling effort comes. We used a Neo-Hickean material model, but the key thing is it's not like we did the local effects. It is still a global phenomena because we are only measuring the force versus the deflection on the biological cell. So it was a very good and rich experience. We haven't done much, but now we are thinking of how to bring our computational tools and the understanding we have in the subjects of fluid dynamics with non-Newtonian flows and of course fluid structure interaction to model blood flow in arteries and study any kind of diseases, especially find ways to eliminate or restrict some of these plaque formation, for example, right? So I think, biology or biological problems are very, very rich. We need to work. So this is one example of spending enough time. You cannot just go around. If you want to do research in biological systems, you should stay there long enough to understand and get enough insights into what you are doing.
Thank you, Dr. Reddy. The next question is from Dr. Marco Amabili from McGill. He has just one question. Which one of your many books is your favorite?
Which part of?
Which one of your many books is your favorite? Which is the favorite book? Yeah.
Okay, so Marco is one of my collaborators, and of course the talk is dedicated to people like Marco. He's a good friend and colleague for a long time, and we wrote papers, including that thickness stretch, and he's one of those who did some analytical thing to correlate the results. So I think, I have passion or, this love. When you ask whether I like my daughter more or my son, and I have two, right? Or if you ask whether I like Meera, Rohan, or Asha, the three are on the screen, it's hard to say which one. Liking is, I really like all of the books that I wrote personally, not the ones that are co-authored, okay? Because I put a lot of interest and passion. I had complete control of what I wanted to write and explain, okay? But there are a couple that I co-authored also. I had influenced the co-authors to go along. So I would say three books. One is, of course, the finite element books, two pair, which is linear and nonlinear. In fact, very few books in the land compared to nonlinear finite element book, none of them will do that kind of job because it is a book written for people to read and understand and even self-implement. So there are some good books, but you can only read and not get anywhere because they only write Ku equal to F. They never explain how K came or where it came or how to implement. So that is one pair. Second is the book on composites, the mechanics of laminated composite plates and shells. And that is a really classic because there is no book in the market that covers from A to Z. It starts with, inelastic or let me say, the theoretical developments, anisotropic elasticity, all the way to nonlinear finite elements. In between, I not only include the theories, but analytical solutions, Navier solutions, Levy solutions, then variational solutions, linear finite elements, and it has beams, plates, and shells. So it is, in a way, almost like a encyclopedia, but it is written in a form that people can read and understand. And lastly, I think I'm beginning to love my work on our books on continuum mechanics, and now they are into second edition. And of course, there is still room for improvement, because these days, one thing that occurred to me, and I do have now my former students, collaborators interested in working on these, is to rethink about topics. See, like a Popkovich vector, Galerkin vector, who is using them? Or use this complex variable technique of solving elasticities. So we need to change the contents of these courses. Means we need to change the contents of the books. We need to be working with the society or engineering profession. What are they looking for? Where they find these things that they can use at workplace. So we should spend time, especially those who are writing books, to bring those kinds of tools into the books, not do things that are, very nice looking, like, airy stress function, for example. I mean, it's nice to do, but who is using airy stress function to solve problems, right? So I think, anyway, this is a long answer. In the process, I gave some ideas to prospective authors. So Marco, I think, I stated at least 3 different books that are my favorite. And so because plates and shells, finite elements are my heart. So those are the books which reflect that.
Thank you, Dr. Reddy. This next question is from Dr. Glausio Paulino. He has a question. Okay, I have a question about early career risk-taking in research. Most assistant professors tend to be very conservative in research in order to get tenure. Should they take more intellectual risks?
Yeah, okay. Glacio is a very close and good friend of me, and he's the one of those who was so excited when he came to know that I was going to give this webinar. And he's a model researcher and passionate, as passionate as I am in research and teaching. He develops new courses, up-to-date type courses, especially on origami. So I think this intellectual component is, I agree, it's lacking in some of these young people, partly because the system is making them. I don't want to fault these young people, because the system is asking only things materially, a lot of papers and money, especially money. And in the process, they have family to take care, and they're, young and building their family, and they have only so much time. And then, so there is always these shortcuts they take. Unfortunately, they may even shortcut teaching. Just about the time, few minutes, go to the class, they take, where is my book, or where is my computer, walk to the class, and they're thinking what to teach that day while setting up, right? So this is not the way. And same way, intellectual component of the doing research means really going to the roots of who did what. We are not doing that much. And in fact, there's a lot of propagation of errors in citing. You just cite, somebody cited it, and you don't even read that paper. I think this is not good either. So I think, when we use this, phrase intellectual, but what we mean is putting your intellect into trying to understand the problem in a way that you feel that there is something, critically, of course, at the same time, with a view to improve it. Like I said, that is what we are doing. All research is to improve in what we know already, and especially challenging ourselves where not many people are working and making a contribution to that. So, I mean, we can talk a lot about this intellectual component, but I think that, again, I don't want to be critical of young people, and I really, every opportunity I get, whether here or anywhere I travel, I talk to them with interest. I tell them to focus on their, passions in life, that is teaching and research especially. And I also guide them in terms of taking care of the family, especially if they have young children. Never overlook them, or grandchildren, because once they grow up, they don't want you near. Okay, so you have to do the right thing, right time. Okay, thank you for asking this question, Blasio.
Thank you, Dr. Reddy. It's very interesting that you brought up family as well, because there are a lot of questions related to that. So these are actually related to questions from Doctors Ramana Reddy, James Hubbard. Do you have a simple model to balance the teaching, research, service, and family life?
Well, you asking for a formula or what?
So what is your approach, at least, on balancing all these points?
I think. Now, by the way, this is a good time. Thank you, James Ramana, and I think I won't hide my deficiencies at all. So, as I mentioned, my wife has been the major contributor. Right, her name doesn't appear on any paper. I don't even acknowledge, other than in few books where I dedicated. But there is really, I have had the fortune to not worry about a lot of things with regard to family. And when I'm needed, she tells me and I obey. This is the most important lesson that you should learn in life. That means when your spouse, in this case wife, tells you something, you must do it. Because they don't ask too many times. And when they ask, if you don't do it, then that is lost. So that is one, and I have taken care. I mean, in the beginning years when she came to this country, she was not able to drive, right? So I would take her to, buy groceries, take her to, driving tests or whatever. So the times dictate what you should do or what is expected of you in terms of your responsibility to your spouse, to your children, and then grandchildren. And then there are social events that you never underestimate the value of. You never say, oh, I'm busy, I cannot join. You have to. So I have done all of those. So that, I think, is the secret of, I didn't do as much work at home in terms of, I used to mow the lawn, all that. And my wife tried to mow the lawn herself, relieving me, but she could not. Then she gave up, and then she hired people. This has been 10 years now. So what I'm saying is I do only necessary, absolutely necessary things that she will come to me. But when she comes to me, I obey. I mean, in a nice way. Yes, honey, I'll do it. Okay. And if I don't do it, I feel bad because she does so much for me. Now, balancing the teaching, research, service, I think every one of them, as it comes, I attend to it. I never try to postpone. Of course, there are always times, and I advise young people to do the same. If your plate is full, you should say no. We have to learn to say no. Okay, especially the service that, people who do it, they get more put on their plate. Whether you are a reviewer or a committee member, if you do it, your job very good, you will get more assignments. I'm not saying you should do a bad thing and get out of it, but restrict them. If you take up, you should do the good thing. You do your job as well as you can. So I think the secret is really in all of this, working hard comes out as the biggest. I'm an average intelligent person, okay? But I work hard to overcome deficiency in comparing to my colleagues like you, Arun, Srinivasa. I'm just putting you guys on the comparison, or James, who asked that question. So, but I think you have to work hard, take things seriously, get on them, and learn to say no when your plate is full.
Thank you, Dr. Reddy. So
But
this
there
next
is no
question.
formula. Okay, I mean these are suggestions and the way I function.
Okay, thank you, Dr. Reddy. So this next question is from Dr. David Valiappan from Malaysia. He's actually an ex-Aggie, one of your students who's very, he's taken many of your classes. So his question is related to teaching. So what is your opinion on the increasing impact of Internet of Things and artificial intelligence in the field of engineering and teaching in the next 10 years?
Okay, so this is good. I'm glad that you're asking because you're paying attention to teaching. And as I always held teaching as a very important responsibility for a teacher. So in the years to come, not much will change in the way of contents, except few examples I gave. But in basic courses at the undergraduate level, the way you teach will change, not so much the contents of the course. Because now we have tools that we can utilize and illustrate and challenge in the way of explaining the concepts and requiring the students to be able to actually test their understanding. So in the years to come, I don't think these MOOCs and other things are the answer. Okay, I mean, I'm not saying you cannot use them. Distance learning only in lieu of, if you cannot physically do it, that's okay. But it never will replace a teacher physically, never. Even a good book cannot replace a teacher. I cannot repeat things that I repeat in a class to make what I'm saying understandable to various minds in the class. Right? I can repeat, but I cannot repeat that in a book. The book is a formal setting. So the teachers are invaluable. They never can be replaced. So going back to the original question, I don't think there would be that much of a change in the way we conduct ourselves, but we will have better tools, better alternatives to explain. The challenge on the teachers is to take interest in utilizing the tools and knowing what is expected of them when they graduate in industry, work in industry. So if you are conscious about that, you will try to bring some of those into your teachings. The fundamental contents don't change, but you are trying to help them get prepared for the workforce. I hope I addressed in some way. Okay.
Thank you, Dr. Reddy. The next question is from Dr. Grama Praveen. In your career, what would you say was the most challenging problem you have solved?
Well, I don't think I solved anything that challenging. I can just go back in terms of, see, this the shear deformation theories that comes to me only because, but it is not a challenging thing. It just came very naturally. It's not like Ramanujan writing all these partitioning of equations or finding the value of pi to the millionth decimal place or something. Nothing of that sort. These are very simple ideas, but I took interest and they did pave way for other people to expand and utilize. So I think it is the impact sense I consider those are very good works. The challenging thing is mostly my students solved, or for example, the refined shell theories. I can think of the lords of shells. I want Roman Arciniega and Greg Payette, and I'm mentioning names now, and Miguel Rivera. These are the lords of shells because they, although I worked in that area for a long time, they are the one who implemented. So the challenging thing in all of these is not just writing the mathematical models, but implementing to get realistic results out of them. So in terms of mathematical rigor and the complexity. I would say the mixed finite element approximations was the most challenging thing I worked, because I don't think it is still solved to the extent for nonlinear problems, because mixed finite elements means using different orders of approximation for displacement stresses at the same time, and able to show that the solutions exist and they are unique. And of course, once you bring the nonlinearity, uniqueness is gone through the window, because they're not unique, and you can only show the uniqueness under certain conditions, in certain contexts. But I think, and lately I started working on another area. This is I think, latest passion. Somehow I have to thank COVID-19. Most people don't, but in a different way, because I was confined to my home office. So I started thinking about what is this finite volume technique that people are so excited about. And then I found some way to bring the positive or the exciting features of finite volume and finite elements into one computational technology. So that is another thing. Again, I won't say it is the most complex or most challenging thing, but I think novelty-wise they are. So I think the answer to your question is, I don't think I have done anything that is so mathematically complicated or difficult to solve, especially after being solved. I mean, if somebody reads my paper on this higher order, third order shear deformation theory, they will say, oh, that is all. How come I didn't think of it? Okay. So that, I think, is what happens with many things, even the so-called complicated, challenging things. After it is shown, then you realize it's not. So getting the idea, that is the main thing.
Thank you so much, Dr. Reddy. The next question is from Dr. Tom Lacey from Texas A&M. So what are your top professional priorities for the next 5 years?
Well, my priority is to continue. Okay, so until physically I fail, I'm going to continue working with colleagues like you, Tom, and we have a lot of things to do, and especially in some of the topics I mentioned, whether it's architectural materials or high velocity impact or damage and fracture in materials, and also, fortunately, we have background and core strengths among our team to pursue things that are, very challenging and useful to industry and government labs. So that, I think, is the most important thing I have. My remaining life, professional life, I want to focus on technological problems of interest to the DoD type agencies in the United States. And also, many of these are for bettering the human life, not necessarily on the war front or anything. So that is somebody else's job, but we need to address these problems. So I think now the problems becoming more challenging only because we are learning that these problems do exist. They were being brought to our attention. So answer to your question is the problem that we have undertaken in the last year or so, and latest one is to really address. I won't talk too much about those technical details, but they are very challenging in terms of understanding the interaction between the solid, fluid, and soil interaction. So these are, soils are very hard to understand, and especially they change from one physical location to the other, not too far from each other, within meters. And also the environmental conditions, like you have snow or all kinds of debris. So how do you really, if you were to drive a vehicle on that kind of terrain, how do you address those things? So I think there are a lot of challenging technological problems to address. And then this whole field of biological systems. At the moment, I don't have any project, but that I think is a very, very challenging area.
Thank you, Dr. Reddy. The next question is from Dr. Shailendra Joshi. He is asking, can you highlight the role of hobbies beyond research and teaching? Because he's noticed you work, but he also notices that you have time to pursue hobbies as well.
Oh, I missed the role of?
Can you highlight the role of hobbies, pursuing a hobby beyond research and teaching?
Oh, okay, I see. So, very good. By the way, I think Shailendra, we used to have fun in Singapore. Now you are in Houston, but we don't see as much. I used to see you more there. My hobbies is I do watch movies. You know that? A lot of Indian movies. In fact, I have probably a lot of extra knowledge compared to many people of the same kind who do research. I can talk about Devanand, Raj Kapoor, people of that kind. And then I also have a lot of, interest, hobby in photography everywhere I go. In fact, my good friend CM Wang always say, oh, Jane always wants to capture every moment, everything in nature. Because I really love nature. I take pictures of anything and everything. I have thousands of pictures in my computer somewhere. And of course, my family doesn't like because I'm always leaving them there while walking and taking picture of everything, a dog, cat, everything, flowers. And then I also have interest, a hobby in music. I really listen because of my multi-processing capability. I can sit next to my wife and watch a TV with her and either grade a paper or evaluate somebody's resume or find mistakes in the manuscript I just completed. And then she will ask me a question if I'm paying attention. To her surprise, I answer her question. Okay, so this multitasking has been very good to me. So coming back to the hobbies, I do like walking, in fact, I want to do that before the classes start. I have to go somewhere. So I have a lot of these hobbies, especially nature walking. And then the other hobby that I have, I don't do that as much, is having people to my place, colleagues. Over the years, I think many of my students remember, we had many parties, get-togethers at my home. And so, we are not same young people to entertain, but we have done that also. So I have hobbies as if they take away my time. No, I do enjoy every one of those hobbies in ways that are possible. So are you looking for any other hobbies, Shailendra? I think that is about it.
Thank you, Dr. Reddy. This next question is from Dr. Paul Spanos. So he's asking, in terms of modeling, are you more impressed by Newton or by Maxwell?
Okay. Hey, Paul, you always ask these kinds of questions, pitting against each other, don't you? Right? Paul Spanos from Rice University is another good friend. He's the editor-in-chief of this International Journal of Nonlinear Mechanics. I'm giving an advertisement here. But I thank you for having a special issue in my honor. I was very taken back by the kind preface produced by Aluru Narayana and Marco Amabili, two co-editors. I think I'm more influenced by Newton than Maxwell, although Maxwell's writings are, I think, less political. I would say that a little bit. If you read about Newton, of course, he played games. So, but I think I'm more influenced by his writings. And in fact, there there are, of course, I would say Timoshenko is one of my heroes because of mechanics connection. And lately I found, because of another colleague from Florida Atlantic, that Timoshenko beam theory is, after all, is not just Timoshenko. It was co-authored with another person. So these are the things that are coming to light, but we need to pay attention to the history and give due credit. So anyway, I think I answered Paul's question, right? Newton is my choice between those two.
Thank you, Dr. Reddy. This next question is from Dr. Sivakumar from IIT, so one of our friends. So how do you keep up your motivation if there's little reciprocation from students, especially from the undergrad levels? Yeah?
Oh, that's Siva is asking from all the way from India, IIT Madras.
That's
Thank
right.
you, Siva, for logging in. And Siva himself is a model professor and administrator. He's a dean of students, very kind and giving person. I don't know, you asked me that question. We should learn from you. But the motivation, I think, is the passion you show. I think the students are not dumb. They can see you. When you do a bad job of teaching, they can see, on a given day, not only the whole semester, but on a given day, you walk in and you just scribble on the board and then keep writing on the board without talking to the board, showing your back, whether you have a new shirt or something. So they know that you are not paying attention, right? So motivating the students come from now and then saying technically something that captures their imagination. Okay? It may be a joke, but still connected to what you're talking about. Okay. So just like I made a comment about Timoshenko beam theory. So you must just bring that, by the way, this is known as a Timoshenko beam theory, but it is not just Timoshenko, right? Or you say Minlin plate theory, it's not just Minlin. So we are really in a hurry to give names, especially in the West, even though the works have been done long before, sometimes even centuries, okay, by other places in the world. We have not rewarded or recognized those people. So coming back to your question, motivating the students really comes from saying things that really attract their attention. And of course, one thing for sure is don't go beyond your 50 minutes talk, lecture, because they don't have the attention span. If somebody stood up, then you know you must quit your lecture. And I'm not very good at that, but because I get carried away. I talk, I explain until somebody stands up. Then I realize I pack my books or whatever I take to the class and leave. So, Siva, I think this is not easy. The question you ask is not easy, and you have to find day in and day out things that really, at least 10 to 20% of the students get excited. You cannot motivate and excite everyone. That doesn't happen simply. But I think even that, 10, 20% getting attention and learning something from you is a great contribution.
Thank you, Dr. Reddy. The next question is from Dr. Mateo Lopez. So he was mentioning that you've talked about research in fields which have not been saturated yet. So what are the kind of fields that you're recommending for the next few years to make an impact?
Yeah, right. I think I mentioned biology and material science at different ways. Material science is not my subject, but we study what is already produced. So that means mechanics of materials. So whether it's architectural materials, metamaterials, or what kind of new mechanics aspect, mechanisms these materials show, which you don't see in other materials, that are especially the natural materials. So you need to get into that. Think of architecture, a beam. And if we use a homogenization and use a beam theory, without using this non-local effects, then this point rotation is not meaningful because nothing is rotating. Whereas if you think of a point in through the thickness and using micropolar theory, the rotation there amounts to the segments that are there in the architecture being either deformed or moving, rotating, right? So there is a connection. So it is only a model that can capture. So two areas that I think are rich in the years to come: biology, biological systems, and the new material systems. Let material scientists come up with them, but we should try to see how we can utilize them for engineering applications. That means engineering the materials in a proper way for good functionality and robustness, and of course, ultimately their fracture or damage or residual strength of these structures. So the two areas, okay? So those are two, and in coming, I think that is Narayana asked about that. Next, I would say, yeah, 50 years or 100 years. So the physicists are also helping us, but I think a lot of experimental work needs to be done. I'm sorry I didn't mention this, because these systems, when we talk about biology and materials, experiments are very, very important. Computations are very, very important. But these two have to go in hand. That is, in fact, we should really train and produce more experimentalists than we are doing now. Because of the very fast pace of our publication, all that, many of the young students are really trying to do thesis or dissertations in more computational or theoretical mechanics. I think we should encourage enough people to work on experimental side, and better is to have both to the extent possible. That means we should train people to have their hands dirty and also do computations. That is the most ideal setting.
Thank you, Dr. Reddy. The next question we have is from Dr. Debjyoti Banerjee. What are your thoughts on the effect of H-index and other citation indices on the research culture, and how this is going to affect the community of researchers going forward?
Yeah, I briefly touched on it. Unfortunately, I think there is a lot of, I don't think in the beginning the impact factor of the journals came for this kind of purpose. We really took it from that and try to use it as a measure of your impact. So just somebody publishing in a high impact journal doesn't make their work is impactful. That's the first thing you understand. Second, you must also know, I need to pick some examples, but not with a bad intention. There are several journals of mechanics related. They have gone from impact factor of 2 to 10 or 13, just like our grade inflation. So what is happening? So it is being gamed by either authors or the editors themselves. And there are a lot of good editors who are not doing that. So I'm not picking everybody. So if you tend to use that as a measure and forget about the true passion you have for the topic and inquisitiveness, feeling that you are trying to figure out something, or find something and explore something, and only think of, how I am going to get my work published in this high impact journal. So that is really end justifies the means approach. That's not the way to go. You must spend time, rather I kept using the word passionately, to determine what is your contribution, how it is going to make a difference, and how it is ultimately helping that particular problem area for the benefit of others, how others, for example, if you solve a problem, by the way, there are some examples in the literature. If some problem is solved, it is closed, right? Nobody's going to reference it because there is nothing more to do, right? Only if you leave it open. I'm not saying that should be a tactic. That means you have to work on a problem that is not closed. You are making contributions so that other people take next step and next step. And most of the problems are of that kind anyway, other than very few that have a closure. And then those, even though monumental work kind of closed, but they don't get cited because nobody is working because there's nothing to work on it. So going back to the citations and impact factor, and I even add one more thing that James may not, I think he tends to agree, is NAE, National Academy memberships. Oh, we have made these things so big, much bigger than they are worth it. Because people around the world, they only pay attention to what you did, not what award you got, what membership you have, what research project you worked on, what did you do with these projects, or what did you contribute to the world, or to the community of that scholars, researchers, how they are able to utilize that and go next step. So in summary, I think impact factor, citations, all that, they are a measure, okay? I'm not saying throw them out, but don't put your effort to only make them look bigger. And I know many good colleagues. Truly, their citations and the citation index is not that big, but I know they did good work. And that good work is not just me, and it shows up in terms of other people appreciating. By the way, one other example I give in terms of citations and H index, all that. My books, some of them get citations, but many of them don't, because take my finite element book. It is cited, but nowhere near the book by Zinkiewicz. But I can almost guarantee, I don't have any way to physically guarantee, that my book is used by many people who never ever read Zinkiewicz book, because there is nothing they can understand by reading that book. I'm sorry, I'm not putting, he may come out of the grave to say, JN, don't say that, okay? But the fact is, it's a very good book for those who already know the method and go on to read more and understand, get some ideas maybe. But I wrote the book to teach the people who are interested from the A, B, C, like that. So it doesn't go to Z because I'm only trying to teach them beginnings. But many of these people, they never even go to master's degree, less to PhD. And then many of them go to industry. Then they never have a chance to cite it. And then those who go to PhD and write papers, they won't cite it because it's not that fancy to cite a textbook. They want to cite a book that they consider as a reference book. So mine is not a reference book, it's a textbook. So you can see the citations is not the best measure. Zinkiewicz book has many, maybe order of magnitude citations than mine. But I think it has helped at least 3 to 4 generations of people who read it. And now I meet people, I've been meeting for the last 10 years, full professors who tell me that they learned finite elements from my book. Of course, this is not a time to, be less modest about it, but just I had to say in the context. But so going back to this, answering the question related to citations and H index, please don't make it such a big deal. While you get it, that's okay, but don't do anything artificial to get them. Don't, every time you review a paper, don't ask the author to cite your paper irrelevantly. I review a lot of papers, and if there is something so directly connected to one of my paper, I only just say, you may have read this so-and-so, but you should understand this is already pointed out or done there. By the way, one time I have an example. I mentioned about these 7 dual variational principles, 7 primal, and there was 5 or almost 10 years later, there was a paper published in Journal of Applied Mechanics on a very variational principle that was in the book. Exactly same equations, everything. And so I, in a friendly manner, I sent an email to him, not to the journal. So saying so and so, do you know that this equation is this equation in your paper is exactly this equation in our book? And the person wrote me back saying that thank you for sharing. I didn't know, and I'm sure I believe him. And this happens. Okay, I don't think people, vast majority of the people are good people. They don't do things to fool anybody. So I'm of that opinion. So, but that can happen. Okay, so anyway, I think the contribution is more important than only paying attention to the citations and H index. They will come. I didn't work on them artificially. They came largely because I published a lot. That's, of course, one element. And then second, of course, I was doing things that most people can feel that they understand. See, that is another thing. If you publish in Journal of Fluid Mechanics, and they want very fundamental fluid mechanics thing, and I don't know if it has any more than 2 impact factor, but that doesn't make it any less than one that has impact factor of 13. Okay, it is a very good journal. So when very few people do those fundamental things, and they don't get cited easily, because you have to do, again, such a very fundamental work to be able to cite it. So there are a lot of aspects to the citations. So if we use that measure in a blind way, it is not good. And you might be destroying or really hurting young people with these kinds of measures.
Thank you, Dr. Reddy, for a very nice reply. The next question is by Dr. C.W. Lim. It's a very interesting question. So everybody believes the result of experiments except the experimentalists themselves. Nobody believes the results of computational simulations except the computation analysts. What is your opinion on this statement?
Right. Well, Chiva, thank you for asking that question. This is coming from City University of Hong Kong all the way. He's my collaborator, by the way. We have written a lot of papers. He has written a lot of papers, and I'm a co-author. And this is an excellent question. So I think we are human beings. We make mistakes no matter what we do, whether it's an experiment or simulation or theoretical writings. So one thing that we must understand, especially in engineering, there are other people who can check that. Unlike in chemistry or biology, because a lot of other things can happen, the compositions may not be exactly what stated in a paper. But if you said enough, people have the ability to reproduce that before they go on to extend it. So the main question that you have, I think there is, I tend to agree with Chiva, C.W. Lim, that most experimentalists feel that what they're doing is right and everybody else doing is wrong. I think that is a wrong thing to hold on to, because they can make mistakes. They may not know that they didn't remove the rigid body mode in an experiment while they're doing the experiments, writing the displacements, things of that nature. So understanding the theoretical mechanics or your subject very well is the most important thing, whether you become an experimentalist or a computational person, because those are your guiding, subjects that will allow you to question the authority, so to speak. So you should not take the position that what you do is the best, others are wrong. So the same thing about computational people. In fact, sometimes I joke, when I see my results are so close to experiment, I immediately tell them I have not purged it or manipulated my results. And in fact, most of the time, they are not exact on it. They are close, but they are not exactly on it because there are so many uncertainties in modeling. The most important thing that we don't fully 100% control is material properties, right? And second important thing is the way the test is actually being done, how they support it, how they apply the load. So we talk about displacement control, load control. What is displacement control? How is displacement comes without a load, right? So what I'm saying is I think people should be more focused about doing things right rather than put their own work on pedestal, put others on in our way. So I think we need people who do experiments. So we should take their heat nicely and say, and some time to time, you explain to them that what you did is wrong. Like I talked about this biological work that we did with respect to the cell simulation, indentation of the biological cell. So I think the people do make mistakes or not make mistakes, but they don't think what they're measuring is not exactly what they think they are measuring. You understand what I mean? So there is always this problem. So, and a true person who is very knowledgeable about things never say that their work is right and others is wrong. When their work and other people's work don't agree, then they try to first check their own work. Then when they exhaust any means, then they nicely, humbly ask the other person, can you please check? Something doesn't check with mine. There is something, can you? So it is really investigating. You don't blame somebody for disagreement. And it may turn out in some cases both are right because the analysis did not account for what experiment accounted for. So within that context, the analysis is right, but it is not, he or she is not doing the analysis of the what experiment doing, right? So I think this will go on. Shiva, he cannot go on to change everybody's. The people are involved and people have egos and they do continue to do what they think is in their best interest. If they are focused about science, they will not take a stand on one or the other. They try to understand the scientific aspect of what they are doing.
Thank you, JN. This next question is from Dr. Dimitri Lagudas. So do you have any additional thoughts on mentoring junior faculty by senior faculty to enhance their professional careers?
Yes, Dimitri. Dimitri is my colleague and he's Executive Dean for Research at Texas A&M. And thank you for logging on too. He's also my collaborator. Yeah, this is, I think, is a very important. I really put a lot of thought into this presentation to bring all elements that I care and really truly believe in. I think it is a very important responsibility of especially senior faculty to mentor not only their graduate students and postdocs, but also junior faculty. And now in these times, what is happening is many junior faculty come on board with a thinking that they know everything. I mean, I don't want to put everybody in the same basket, but there is that tendency. They want to start a new journal or start a new center, and they think that is a quick way to get to fame. I try to tell in a nice way. Sometimes I take them to lunch, and first thing I tell them, they should not be here if you're not interested in teaching. That's the first and foremost thing I tell them. Then I talk about how to manage teaching, research, and service. And I tell them in no ambiguous words that teaching is something that they have to take it seriously. So the mentoring is really something you take their interest and their welfare, they're developing them into a good member of the community into consideration and advise them. Not necessarily it is my way, your way type thing. So this is where chemistry I mentioned comes in. So you have to get into their confidence. And that comes by, having the right chemistry, showing that you care, not by filling the forms, because we have those forms and there are rules how to mentor. That's not how it works. I think a lot of people seems to follow, go onto website, download something. Oh yeah, this is what mentoring is about. Okay, reading them is okay. I'm not saying wrong, but you really have to have your heart into it. Help them truly interested in advancing them. And again, it doesn't mean you have to put them as a co-author or put on your grant. That may be a part of it if it is suitable. Not, you never, just like I mentioned about giving help to students, you should never make them parasites. Don't unnecessarily put them on your grant if they are not able to contribute to it. That's not really good mentorship. So the mentoring is really a chemistry and your interest in them being developed into good colleagues. So I think I think I have said enough without repeating too much. So I hope, Dimitri, you get what I have in mind.
Thank you so much, Dr. Reddy. I think we'll answer one last question before we call it a day. We have to give you a rest as well. Is that okay?
Yes.
Okay. The final question is, how do you write a textbook that students feel so much easily to go through it and for self-study? This is a question from Singapore, yeah, by Dr. Hua Lee.
Okay, thank you. This is not an uncommon question. I already mentioned, many of them ask me how I wrote it. But then they also ask me, how is it possible that you explain so well? So the first thing is really I try my best to practice that by teaching. So because these books came out of teaching. And I learn, every time I teach, I learn how to present same old thing. Every time new people, new intellectual capabilities, new way of looking at the same old thing. So to the extent possible, I take, and because like I said, book is a formal presentation. I cannot repeat sentences, right? So what that kind of ability to, or interest to explain things to students naturally go into these books. And one other thing that I do, again, probably partly it is because I'm not so smart. So because I want to understand, if I don't understand, how can I explain to others, right? So that is the foundation on which I write things. I explain to myself, is this the right way to explain? And I practice that through teaching. And if it works, and it ends up in the book. And of course, by the way, we are all, every one of us have different DNA. And a good majority of the people, thanks to the courses they take before coming to the courses they take with my books, I definitely depend on those. If they don't have that background, they will find difficult. But one other thing, secret, I don't want to say it is a secret. One thing I try to do is self-contained. I never write appendices, too many. In fact, I don't think any of my books have appendices. Only nonlinear FEM book has appendix only for solution of nonlinear equations, something like that. But even that, I explain inside the book. For a Rick's method, which is more advanced method, I say go to that. But all of other books, I never put something there and say go read it somewhere. So I try to make it self-contained. So that is another reason why students or readers follow it, because I'm not leaving anything that is not explained.
Thank you so much, Dr. Reddy, for a very concise answer. So before we conclude our special seminar today, so is there anything you would like to share with us? Some final thoughts before we close the session? And I can see Dr. Srinivasa is there as well.
Right, right. Well, my final thoughts, in addition to wishing every one of you and your families safe and having peace and happiness, you must take, we are here only short time in this world. Really, our lifetime, entire lifetime, and not because I'm old, your entire lifetime is a dot in the continuum of time. And we should take pride in what we do. And that, I think, is, you might say, oh, it's easy to say. Well, you have to practice. You have to find motivation to like what you do. Because after all, you're putting a majority or quality time every day in that, in addition to eating and watching TV or being with the family, you are spending a good amount of time, anywhere 6 to 8 hours, some of us 10 to 12 hours, but you must enjoy that time. When you do that, I think you feel that you are doing something. And of course, at the end of each day, you might also ask, just don't put yourself down. What did I do today that was of some use? Okay, at least once in a while, not necessarily every day. So that way you kind of gauging yourself. And it is important to understand that you have to stick to your, whatever that passion is. Don't try to imitate and use political ways to expand your horizon. Only if you are able to do it and you are able to make a contribution. If you only think of, oh, how do I publish in that area, in this area? Well, you'd collect no mass. So you just go on to publish, but nobody identifies you with a topic. And that comes only by being in one area, making a contribution. And that takes time. So all the best to every one of you. With those thoughts, I hope to see you at the conference, if we can make it, in March of 2021. Otherwise, I'm hoping that I would be coming to see you wherever you are. And I'm excited that there is a lot of life ahead of me. And so please take my best regards to you and your families, and take care. Bye.
Thank you very much, Dr. Reddy, for very nice words and very immortal words and advice as well to all of us. Yeah, I guess we should follow our passion in life, and you should always like what you're doing. Yeah. So I want to wish you on behalf of all of us, we'd like to wish you a very happy birthday again from all over the world. Yeah. So this is truly a global phenomenon. And Dr. Srinivasa, you wanted to add something?
Yeah, just wanted to say that first, thank you, JN, for sharing the first 75 years of your life experience. So we are looking forward to the next 75. Also, Dr. Was and JN also mentioned that he likes photography. So it would have been fabulous if you were able to photograph all the nearly 300 people who attended this. So please make that possible by coming to the conference. And thank you very much to both Raj, Kota and Prakash for running this conference with this kind of professionalism and so on. And last item is thank you, Nicole, who helped us set up the WebEx. Thank you very much, and have a pleasant have a pleasant day, depending upon where you are. It's either morning or night. Thank you. Bye.
Thank you.
Thank you, Dr. Srinivasa. So with that, I would like to conclude by, it's a very nice statement given by Tom Lacey. It's a long comment here. He says, Dear JN, I wish you a very happy 75th birthday. You have established a lasting legacy of excellence in research, teaching, and service. What is more impressive is your legacy as a wonderful and giving human being. So it's a very nice way to end this birthday talk. Thank you once again. Happy birthday. And good night, good evening, good afternoon, wherever you are in the world. Thank you so much.
Take care. Stay safe.
Stay safe.
Yeah.